in our universe, as well as the fact why there's dark matter, what is dark matter made of. But these two last points I won't be discussing today, actually. I rather focus on the flavor sector, and I would like to add another points to the flavor sector and to the flavor puzzle, so to say. We all actually like to go beyond standard model, and we know that these theories have a very rich phenomenology, in particular, if we look at what is called the flavor sector. So you know very well there are processes forbidden or highly suppressed in the standard model, which you can easily produce or easily generate in beyond standard model theories. One prime example is what is called mutate gamma, and we currently have this limit here from the MAC2 experiment as PSI, and this is not the only process we have to keep an eye on. Indeed, if we look at beyond standard model theories, usually the flavor and also the CP sector means then observables like the electric dipole moment of the neutron or of the electron can easily be generated way above the current experimental constraints. So we do need to keep all these effects well under control. And the third point is you can be more optimistic in the sense of just not only passing limits, but you can look towards the future, thinking that there might be some of these processes actually being observed, and then you would like to have some underlying principle, whatever, which gives correlations between these type of different signals. So all on this slide, actually, for me personally, is pointing towards some symmetry, some additional organizing principle that should be there in the flavor sector. So, and I would like to put my bets on today on some symmetry, and we say because I would like to be inspired by the fact that gauge symmetries are very successful in nature and describe many effects in nature very well. So we would like to impose a new symmetry, which now actually acts on flavor space. And here is a little example. So this is very easy to get just an idea. So imagine that you take the 3 generations of the quarks, and you just say, okay, let's permute them and see what happens. So what happens then, your mass matrix for the quarks has to have a special structure, and this obviously has an impact on the quark masses and also on quark mixing, what you would observe. So if you take this symmetry as exact symmetry, you most likely would end up with a quark mass spectrum, which actually is not compatible with the one we observe in nature. So that's kind of a hint, and this is also what we actually realize where we carefully look at the data which we have, so fermion masses and fermion mixing, that we do not see really an exact symmetry. So what we think, if there's a symmetry, that this is a symmetry that's at the very low scale at which we are looking at the data is going to be broken. So then the next step naturally is, if you say, I accept this kind of new organizing principle, the symmetry, you ask yourself, okay, what could be the possible properties of this symmetry? And so these are just some examples, not even exhaustive, but just highlighting some prominent features which you usually can have a look at and consider. So it could be an abelian symmetry like a U1, as we know, or non-abelian like SU3, could be continuous or could be discrete, could be local like the gauge symmetries, or just a global symmetry. And as we were just saying, at very low energies, there seems to be no immediate trace of flavor symmetry. So we believe that it should be broken, but we actually also do not know the way it's broken. So broken explicitly or spontaneously, broken in some arbitrary way, or some residual symmetries, at which scale it's broken, neither we do know this. So these are all points which we actually have to decide on before going forward to looking at some pheno. So I would like to highlight my preferred choices, which I will keep today in this talk. So I would like to have a non-abelian discrete symmetry, and I don't want to break it arbitrarily. And here are some keywords like for my motivation. So for example, so why do I like non-abelian symmetries? So we were starting off the talk by saying there are 3 generations. So if I want to explain why actually they all come in packs of 3, I'd rather have to have a non-abelian symmetry which has irreducible representations, which can also be 3-dimensional. So then the discrete choice is rather because discrete symmetries, as you know, if you just think about some crystals or whatever, they usually have preferred directions. These preferred directions are very helpful if you want to describe mixing. And then the last point is like this breaking, why shouldn't it be just arbitrarily, but rather to some residual group in some sector of the theory, but that's just to increase the predictive power. So just that's the rough idea of why I would like to keep to this context. So if you now are still with me and say, okay, let's try this out, this possibility of non-abelian discrete symmetries, you can ask the next question. So how many of these do we have at our disposal? How many options are there? And indeed, this is a non-exhaustive list again. So, and you see already there are different series of symmetries, which have been discussed in the literature. There are like different groups, like symmetric groups, alternating groups. S3 and S4 are among them. A4 is among them. There are these discrete subgroups of modular groups. There are also new advances in this direction of modular symmetries in general that are generalized forms of flavor symmetries. There are these sigma groups, which are sort of like equivalents to the exceptional Lie groups, if you want. You can think about adding other type of symmetries, which are not only flavor, but also CPsymmetries. And here's my preferred candidate for today. This is the series of these delta groups, and I would like to add also CP. So I will give you some very brief introduction in the following 2-3 slides to these delta groups, and hope to convince you that it's a good idea to study this series of groups. And also will give a brief intro to what I think are the basic units for the CP, which I'm going to use in the following. Okay. So now let's first come to the series of the data groups. So why are they interesting for me? They're interesting because they offer 3-dimensional irreducible representations. So if these allow me to pack all the 3 generations in one irrep, so I can explain why there should be 3-dimensional, why there should be 3 generations, why they come all in 3. If you are not happy with just packing them, all of them in 3, then they also have 1- and 2-dimensional irreps. So that's kind of, it offers a certain flexibility as well. They are actually series of groups. So, and they had many things in common. So one thing that they all have in common, they are subgroups of SV3, which means we actually know very well how to handle them. They're easy to handle. They can be nicely described in terms of 3 generators, which are A, C, and D here in this representation, and they fulfill these relations. So what is nice about these A, C, and D generators, then it allows you to write uniquely every element of this group in this form here. And to make connection to some very well-known groups, so if you choose n equals to 2, you get delta 12, and this is actually isomorphic to the group A4, which is probably the most used and prominent flavor symmetry, and is responsible for trial maximizing. And so that's so much about the delta 3 n squares. If you want to go to delta 6 n squares, so still everything here is also true, you just need to add 1 generator. So this is the generator B you need to add to the ACD, which we had before. Again, it fulfills a bunch of relations. And then you have to have the possibility to write each element of this delta 6 n square groups uniquely in this form of A, B, C, and D, and some powers. Again, if you want to make connection to groups which are used very often, in particular in the description of lepton mixing, take n equals to 2, and then you get delta 24, and this is isomorphic to the permutation symmetry S4. So now we have settled the part with the flavor symmetries. Let me keep going on with the next symmetry, namely now with CP. So CP you all know from your QFT classes. Here actually we use something which sometimes is called a generalized CP symmetry, but actually it's just the most generic way of defining CP symmetry. So you imagine you have a certain bunch of particles, so copies of a certain particle species. Imagine these phi's are just scalars, and then they have an index I. So you have maybe n of these. And what you can do, you can define the usual CP, which you know from the textbook. You can also say, I can define CP in a way that it also acts in the same time on the flavor index here, on this label I, which now can become J. So, which means I'm intertwining here the action of CP with the action on what, in regard of the symmetry we are interested is called the flavor sector, so the flavor space. So, and then I have this matrix X, which kind of be maybe just a permutation matrix, maybe it's something more complicated. In general, it's a unitary matrix. And since I would like to focus on CP being an involution, it's for me always a symmetric matrix. So I don't have just XX dagger being one, I have XX star being one. And if you now ask yourself, how can I choose this X? Or is there some kind of catalog or whatever? Mathematically, this type of CP symmetry, it corresponds to an automorphism or the flavor symmetry. So that's, once you know your flavor symmetry, you just go to the mathematics and then you check out what's the automorphism group of this flavor symmetry, of this discrete symmetry which I'm using, and then you know what are the CP symmetries which you can use and combine appropriately with this flavor symmetry. And let's come to the third point. So I was also telling you that we know that the symmetry should be broken. And I actually don't want to break it in an arbitrary way. I want to rather break it in some non-trivial way, which means you see it here on the slide. So what's the motivation for it? So you imagine you start with some symmetry, and then you say, imagine that there's some residue for the charged leptons. Now I do it here for leptons because today we are discussing leptons only. So I imagine that there's here some residue for the charged leptons, and there's another residual group for the neutrinos. So the one I call GE, the other one I call G nu. So what happens now? If I look at each sector separately, these residue symmetry, the GE and the G nu, they just tell me how my mass matrix for the charged leptons and for the neutrinos respectively looks like. This means I can diagonalize these, and from these I do get, in particular, the PMNS matrix, so the lepton mixing matrix, which means the imprint of these residue symmetries actually lies in the fact that they determine how the mixing matrix looks like. So this is very general, and you now can ask more refined questions, which kind of symmetries, residues you would like to have here, and what can they do and what not. So here, for the charged leptons, I prefer to have a Z3. This is the minimal choice simply. And why do I say this is the minimal choice? Because a Z3 is a group which has 3 different charges, which means I can give 3 different labels to the electron, to the muon, and the tau. So actually I can identify them as 3 different particles, which potentially have or usually have 3 different masses, which is what we observe in nature. If I go to the neutrinos, for me here, and in most of my life, neutrinos are Majorana particles. If you then look at the neutrino mass matrix, you see that it's relating this fields of the same kind. So the maximal type of symmetry which you have, it's actually is a Z2. Or let's say powers of Z2s, in the sense like products of Z2s, Z2 times Z2 in case you have 3 generations, in case you have more than 3 generations, Z2 times whatever. And here I would like to also involve the CP because I would like to have a handle on making predictions for CP phases. So instead of using what canonically has been used for 3 light neutrinos, Z2 times Z2, I switch to some little variant here, which is a Z2 times ZP. So what do I get then? I will actually get a UE matrix, so apart from the charged leptons, which determines lepton mixing, and the U, which is the part coming from neutrinos determine lepton mixing, which actually combines here to the PMNS matrix, which has a horrible form for you, but actually you will see it's quite easy because UE is just the matrix with numbers. Also, this omega nu is a matrix with numbers. The R of theta is just a rotation in one plane, and the K nu is just a diagonal matrix which has entries plus minus 1. So what I'm ending up with doing this game is a PMNS matrix which depends on one real free parameter, which means the 3 lepton mixing angles which have been measured, the 2 Majorana CP phases, and the Dirac CP phase, they're all just depending on one free parameter. And these free parameter usually adjust in such a way that the measured lepton mixing angles are explained within their 3 sigma ranges, and then you get prediction for the CP phases. So about our masses, I won't talk much because masses are just free parameters here for me. I'm not addressing the mass hierarchy or anything here at the moment. I'm rather interested really in the flavor structure, which is expressed mainly in the mixing. So this far was now the introduction to the symmetries and to CP. So maybe now, in case someone has a question regarding this part, please feel free to ask.
Claudia, what was the reason of choosing the delta 3n square or delta 6 square in comparison, for example, with the sigma group, for example, sigma 3n to the cube that also has triplet irreducible representation?
Okay, very good. Yeah, I mean, so my aim is not to believe that there are these data groups, that this has to be realized in nature. What I was searching for was a series of groups which is easy to handle in the sense that I can study it well in one shot, that I don't need to focus one group by one. And I also like the fact that the smallest deltas are very well-known symmetries, like A4 and S4, and that we have seen already in previous studies that these actually are very useful to describe lepton mixing. Like you remember the game all started with TB mixing, and then it went to generalizations, which can be realized with other delta groups. And then if you add CP, you can also add very nicely, these automorphisms group of the delta groups are also very easy to treat and handle, and so you can study them in a very nice, complete way. So that's my approach to it. I'm not saying exclusively this is the only series of groups which is interesting. No, definitely, I agree. We should explore every series of discrete symmetries which we have. But yeah, I mean, I find it nice if you have a series that you can treat them in a unified way.
Thank you, Claudia.
Other questions? Comments or anything? If not, then I would say I jump to now relating these general pieces which I was showing, so the symmetries and the idea of the breaking, because that has been studied already 10 years back by us, because we were asking ourselves, okay, if now this GF is one of these data groups and we take one of the suitable CV symmetries, what's going to happen? In the beginning, you might be thinking, ooh, you will get a lot of different results, and probably this mixing can be anything and will look like any type of mixing. No, funnily, actually, you can categorize the different types of mixing patterns which you get from this approach here if you use these data groups in 4 classes if you want. Case 1, case 2, case 3a, and case 3b1, which have different properties regarding the mixing what you get and also the predictions for the CP phases you get. Just to give you a very brief idea, I will not talk about this much, but to give you some idea about how this can look like, let's go to case 1. So in case 1, you will see now the 3 lepton mixing angles. They indeed depend on this free parameter, which I got theta L here. And then you can do something. You can try to fit this theta L such that all your lepton mixing angles are explained well. And you see here, yes, you can do it. These numbers are, if you go to the new fit collaboration to the fit, they are agreeing at the level of 3 sigma at least with what is observed experimentally and what is derived then by global fits. maybe that's not really so the interesting point. Maybe here the interesting point for this case one, which actually is particularly easy, is that it has very stringent predictions for the phases. So it tells you that sine delta, so the sine of the Dirac phase is 0, so the delta itself is 0 pi. The same is true for one of the Majorana phases. And for the other Majorana phase, actually, this depends on your choice of CP symmetry. So this you can then test, the sine delta being 0 with future neutrino oscillation experiments like Dune and Halber-K, and hopefully you could get a glimpse on whether you are on the right track with this sine beta being 0 and sine alpha being non-zero through neutrino double beta decay. This is only the very simplest example. Let me show you also some result for the case 2, just not that you believe that these phases always have to be 0 or some particular thing. Here you have something more complicated, because here you see actually a plane where you have this three parameter theta L, and now this quantity here describes your CP phases, or one combination of the CP phases. So what does it tell you? It actually tells you that you have to be on this arc here in order to explain lepton mixing well. So this is this green or this orange, depending on whether you include the information on the delta phase. And then there's another parameter which also is determined by the CP symmetry. If you want to see some examples in numbers, in terms of numbers, you could fix this n. So this would be the index of this delta group. So imagine you take delta 3n square and the n is going to be 14. And then you will have a certain choice of your CP symmetry. And these are the resulting lepton mixing angles. So here you see considerable differences between what's the prediction for the atmospheric mixing angle. And even more so, you see very nicely that these different choices give you different predictions for sine delta. And they are very far from being just 0. They can be maximal, actually. So you can get maximal CP violation, which should be then observed easily in some of the future experiments. Here, this other parameter, which determines at least dominantly one of the Majorana phases, you can also vary, and then you would get a variety of predictions for this, what the Majorana phase could be, depending on the choice, the original choice of the symmetry. Okay, so now we really turn to the next part, which is a very brief intro to the inverse seesaw. So the inverse seesaw works like this. You take the standard model, you add 3 generations of particles, which I call N, and another 3 generations of particles, which I call S. I admit that this distinction is artificial because with respect to the standard model, they are all gauge singlets. Imagine that we are in some extension of the standard model where you can actually distinguish between these. So I would really keep them as 2 different sets of fields. So then I can write down these 3 types of mass terms, where you immediately spot the first 2 ones are what we call Dirac type masses, and this is a Majorana type mass. So since everyone now comes in 3 generations, this mass matrix turns out to be a 9×9 matrix. And now what's the typical limit for the so-called inverse seesaw is that you assume that this mu s, this is the Majorana type mass parameter. So this is the lepton number violating parameter, is much, much smaller than the electric scale, which is hidden here in this MD. And this is, again, usually smaller or much smaller than the typical scale of the new states of this NNS states, which is encoded here. Then you can reduce what the leading order result is for the light neutrino masses, and this is the mass matrix structure you get here. You can do the same for the heavy states, for this NNS states. You see that these actually combine into what is called pseudo-Dirac pairs because of this hierarchy which we assume. So where you say the dominant mass block is this coming from this MNS, which actually gives you, sets the mass scale of the states, while then you have these states being splitted slightly by this Majorana mass. Now, since we have a 9×9 matrix here, actually our matrixing matrix also grows. It's not 3×3 as you know from the usual PMNS matrix, but it's now 9×9. And the PMNS matrix we rather find in here being the one which is now this one, which approximately diagonalizes or to the leading order diagonalizes the light neutrino mass matrix. And this matrix actually, since it comes in here in this 9×9 block, is not unitary anymore. And for this reason, it's convenient to parameterize it as a unitary matrix, which is this U0, and some deviation from unitarity, where this eta you can calculate independence of the mass matrices, which you have these blocks, which you have the MD and the MNS. So this part in particular is experimentally strongly constrained, as we will see then if we come to a concrete realization. So this is actually all what I want to say to the inverse seesaw. Are there any questions until there? Or if not, I would say we now put all these things together. So putting these things together means we start with the states which we need for describing leptons in the inverse seesaw. So obviously we have right-handed charged leptons, we have left-handed lepton doublets, and then we have this N and S states. And since we now want to add on this, the flavor and CPsymmetries, we have to tell people how these are going to transform under the flavor symmetry. So you see, I try to unify as much as possible I can the three generations into triplets, which means I take the left-handed lepton doublets to be triplets, the N and the S states as well. For the right-handed charged leptons, I'm not going to do this because that actually would usually make it much harder to distinguish and get the mass hierarchy correctly. I won't enter here into details on you unless you ask me for that. Now go to the choice of the three-dimensional representation. I would like to use here what is called an irreducible faithful representation, so which corresponds to the possibility to fully explore what we have seen before as predicting for the mixing. Then combining these here, this 3 and this 1, and the fact that we have a residual Z3 symmetry down here, actually allows me in the basis in which I usually work that this turns out to be right away a diagonal matrix, which has 3 different entries corresponding to the masses, where I told you, I just know that these 3 entries are different. I can't tell you which hierarchy they do have. I just accept this as 3 parameters on my approach. But as you see, this is a diagonal matrix, so it's not contributing to lepton mixing, which means from now on, we actually will forget about the charged lepton sector. That's going to be here not the important part. Now coming to the N and S states, I would like to assign them to the same three-dimensional representation as the left-handed lepton doublets. And why do I like to do this? I like to do this because I want to have that this MD matrix, which we had over here, which comes from here, and also the MNS matrix, that they turn out to be allowed in the limit in which the symmetry is not broken. While the Majorana mass matrix, I can't write down unless I break the symmetry. What is the effect of this? The effect of this is that these matrices, the MD and the MNS, have a super simple structure. They're just proportional to the identity, and I have one overall Yukawa, and I have one overall mass for the heavy states, while the symmetry breaking, and so to say, all the flavor structure is encoded in this Majorana type mass matrix. And here you see this structure, which you have seen already before. This is kind of like how we describe the lepton mixing matrix, depends on this some omega matrix, which is determined by the CP symmetry, and one free parameter, which is just an angle. So now you can ask, okay, if I have these matrices, I can calculate my light neutrino masses. Yes. And you can find out that your light neutrino masses are actually determined by this mu1, 2, 3, which are in the mu-S matrix. So this allows you to adjust the light neutrino mass spectrum as you wish. While what we had before, this US actually turns out to be the PMNS matrix, or the would-be PMNS matrix, which we have to say, because this one we know in the end will get corrected by the non-unitarity effects, which come from the heavy stereostates. So if you want to look at the stereostates, the heavy guys, what do we know about them? We actually know that they all sit at the same mass. This is this M0. And then they are slightly splitted by these small mu parameters. So we are talking about 3 pairs of pseudo-Dirac states, which sit all at the same mass scale models. For the light neutrino masses, you can actually go beyond what I did here, this leading order. And you can calculate what is called subleading corrections to the light neutrino mass matrix. Looks terrible, but actually turns out to be diagonalized in exactly the same way with the same matrix US. So this doesn't change mixing or any other thing what we have seen. It slightly shifts the results for the light neutrino masses, but that's a very subdominant effect. More interesting and relevant is this effect of non-unitarity, as we were saying, that our PMNS matrix actually is a unitary matrix U0 corrected by this 1 minus eta factor, where this eta is written in this way. Now we have the form of the MD and MNS, so we can calculate it. Turns out to be very funnily, in this case, being a flavor universal and flavor diagonal matrix, which is very unique in the case of the inverse seesaw scenarios. So, and it also, as you can see, it's not depending on some of these cases. So it's actually not depending what you actually get for the mixing. It's always acting in the same way. And it actually acts as some overall suppression factor of all the entries of the PMNS matrix. So if you want to say now, what are the experimental constraints on that? Then you have to look at these experimental constraints, which given in some global fits also to this eta matrix, and you spot immediately that the eta mu mu here, this is the one with the strongest constraint, because our matrix is anyway just diagonal. So, and we have to go for the strongest constraint on the diagonal, which is this one here. And this we can use in order to, as you see from this formula, in order to constrain the combination of the Y0 and the M0. So you can imagine you choose a certain Y0, and then you ask yourself, what's the minimum mass scale M0 which I have to use? And obviously, the larger the Y0 is, the larger the minimum mass scale which you can use is. That's just what these plots are telling you. You can ask the next question. So now what we know, we got our lepton mixing before, and now we see that this is going to be corrected by this 1 minus eta factor. And we go back to case 1, and we want to see what's the effect then on the results which we got before. So before you were seeing that the sine square of theta 1, 2 was actually given by this, and we were adjusting this angle to 0.18 in order to get close to the experimental data. So now here we are evaluating for different values of the Y0. What's the impact depending on the mass? So you could say, wow, now you look at the scale, the impact can be up to a few percent. Yes, in principle, but be careful, take into account that there's this gray area, which tells you that for Y0 being 0.5, actually the minimum allowed value of the M0 is going to be around 2.4 TV. So you shouldn't look at everything which is here in this gray area, which means effectively, if you take into account the constraints on the eta, in particular the eta mu mu, as we've seen, your effects on the lepton mixing angles, the perturbations you get from this non-unitarity turn out to be much below 1%. And you might ask, is this true only for the solar mixing angle? No, this is also true for the atmospheric mixing angle, as you can see here. You can ask yourself what happens to some possible correlations which I can have between these mixing angles, because they all depend on one free parameter theta only. Also, these are in the end, if you take into account the constraints from the non-unitarity parameters, in particular from the eta mu mu, you will see that they are extremely mildly affect. So which is, I mean, for me personally, I would say it's good in the sense that the predictions, what we get for the lepton mixing parameters are hardly perturbed, but you can say the other side, okay, you have not much signal, which is actually related to the fact that you have this inverse seesaw scenario. You can go on, ask yourself, maybe what happens to the lepton mixing angles as the perturbation is boring? Maybe there's a huge effect on the faces, who knows? Short answer, no, unfortunately it's not. What you see here is a plot of saying that this sine alpha, as we were discussing, actually is a function of this phi s, and this s tells me what kind of CP symmetry I've chosen. And actually this goes sinusoidally, so I have this kind of sine behavior here. You could ask yourself, is also this maybe distorted in some way by these corrections from non-unitarity? No, the short answer is always no. And whenever you see something as a very visible deviation, as this kind of suppression, then be aware of the fact that we have used an M0, which is pretty small, and while at the same time a Y0, which is very large, which actually would be excluded already by the limit on the eta mu mu. So this is just for showcasing you how the effect would be, but the essential allowed effect is more like being close to here, where the M0 is going to be 5 TeV, and you hardly see any difference between what you would get plainly by this relation. You can ask yourself, okay, maybe we were unlucky with the sine alpha, so with this Majorana phase, so we can go to case 2, where actually we have seen sine beta and sine delta are not always 0, and ask ourselves, are there any huge effects here? No, again, the answer is negative in the sense that you have no huge effects, but it's positive from the symmetry model builder side, in the sense that these perturbations are really small. So we see these imprints of the symmetry still very nicely, and of this approach very nicely in the predictions. And also the other cases you can study in a similar way. I have only 2 slides here on the charge lepton flavor relation for this option, because that's actually a really boring part, to be honest. We just have to remind ourselves that for this option here, I was saying everything which breaks the flavor structure has the non-trivial flavor structure, and is encoded in this lepton number violating piece here. So so lepton number violation and flavor violation in this sector of the neutral states, they come together. They sit in the same source. And then we were saying that this eta parameter is always proportional to the identity matrix. And then there's a third aspect, which we also were touching up on, is that this spectrum of the heavy states is very peculiar, because you have 3 pairs of pseudo-Dirac states, which essentially all have the same mass. So you imagine that we were talking about TV-ish, and this mu is usually EV-ish, KV-ish, so really it gives a very small splitting. So you take all these pieces together, and you take the standard formulas which we have for example, mu T gamma and mu T 3, and evaluate this now, and you get very clear answer, which tells you all charge lepton flavor relation, which we were testing, so the radiative one, the trilepton one, but also mu E conversion, is strongly suppressed. And this is based on these 3 facts which I was presenting you, which means for this option 1, which we were discussing, we are now extremely fine. We are easily passing all the current limits and future limits as well. Nevertheless, you would say it's probably a bit boring in the sense, because it's very elusive, this scenario. So you can just test the lepton mixing parameters, but you don't really have additional signals. And yeah, so maybe I stop here for a second in case you have some questions. No question. So then I'm happy to move on to option 2. That was kind of triggering us by saying, okay, this option 1 is a bit boring, because we really have no signals or charged lepton population. So we were thinking, how can we change this scenario? And this scenario we can change by now assigning the left-handed lepton doublets still to this triplet, but this N and S states to another type of triplet. So here the story is exactly the same as before. As for option 1, the result for the charge lepton matrix is exactly the same. So just keep it in your mind, but otherwise it's not interesting. So what are we doing now here? We use a different type of triplet, and this is still irreducible triplet, but this is in general, it's not what one uses here turns out to be a complex one. Here we use a real one. This is usually unfaithful. What's happening then? So since we are using a real triplet for this S states, turns out to be that we can write this mu S matrix, so the lepton number violating matrix, in the limit in which the symmetry is preserved, as well as the connection between the N and S, so this M and S matrix. So we can also write without breaking the flavor in the CP symmetry, while for writing down the coupling between the lepton and lepton doublets and the N states, we actually have to break this flavor symmetry, because 3 times 3 prime, since they're different triplets, this wouldn't give you an invariant. So the story is here, you can have this M and S matrix without breaking the symmetry, and this mu S matrix as well. They both have a super easy structure, so there's a trivial flavor structure. You only get overall parameters, one M0 and one mu0, while you get all the interesting structure, the non-trivial flavor structure is encoded in this YD matrix here. This might look very terrible to you, but let me remind you that these omega matrices are determined by the choice of our CP symmetry. These are just numbers. This P matrix is also just a number. So if you count, you see that this has 5 real parameters. So there are 2 angles, 2 thetas, and these y's. And let me go to the next slide in order to give you an overview over all the free parameters and all the parameter space which we now have available in this scenario. So we have 2 scales that we were saying. There's this M0 and the mu0. And remember that this M0 actually just tells you how heavy the new states are. This stereostates, this pseudo-Dirac pairs. The mu0 is the lepton number breaking parameter. So this determines how much you break lepton number in this scenario. The 5 real parameters which we get here all in the YD, you can treat them as saying, I use the Yukawa couplings in order to fit the light neutrino mass spectrum. So, and there you tell me, I want to have a normally ordered light neutrino mass spectrum with the lightest neutrino mass being 0 or being, I don't know, 0.03 electron volts, whatever. I can adjust that. Then you have the 2 different angles. One of these 2 angles actually is the angle which we have seen in the beginning, which is the single angle which appears in the PMNS matrix in which we fit, such where we can explain the lepton mixing angles well, and then we get our predictions for the CP phases. And then you have another free angle, and this is a free angle. So this has no immediate phenomenological consequences, so we use this as free parameter and we scan all over it. So that's actually then to give you an idea about the free parameters which we kind of have. These are the 2 scales. And you see here, these are typical values, like something above the electric scale, typically under 10 TeV or so for this heavy state. Then this mu is typically small, as we said, like 100 TeV to 100 keV-ish. And then here, this is the free parameter, this theta r, which is going to be scanned just as an angle it is between 0 and 2 pi. Just as an amendment, if you would like to ask yourself the Yukawa couplings, what are the Yukawa couplings which we typically get here? These are between something like 10 to minus 5, so around the size of the electron Yukawa up to order 1, just to have give you an idea. So, and what you can do then, you can just say like, okay, go ahead, we study lepton mixing, we study charge lepton triangulation, and this we do for the different possibilities we have for the cases. Let me jump over this for the lepton mixing because it's not really very interesting. It's just a generalization of what we have seen before for the option 1. For the option 2, for this other choice actually, where this YD is non-trivial, has a non-trivial structure and flavor space, really interesting are the charge lepton flavorization processes. So let me first, before coming to the numerical results, make some general comments. General comments is like, if you look at these type of processes, like radiative decays, the trilepton ones, the mu conversion thing, you see that in our parameter space, which we're looking at, usually the dominant contribution is proportional to this eta alpha beta absolute value square. So there's mainly one entry of this eta matrix which plays a role. Then another interesting point to observe, which is nothing new, just coming up in our study, but it's known for the inverse seesaw people, is that for the trilepton decays, a mu-E conversion, in particular, if the masses of these pseudo-Dirac pairs become a bit larger, a bit above TeV or so, you get that the Z-penguin contribution dominates. And there's an interesting observation you can make for the mu-E conversion, is that there's always one value of the M0, which depends actually on the nucleus which you use. So we like to use aluminium because the future experiments, COMET and mu2E, are going to run with aluminium, where you can get an exact cancellation in this conversion rate. And this occurs here for the aluminium at 6.5 TeV. So this much now about like the generic features. And now let me just come to the case one, because case one was the one which we were discussing for the lepton mixing. And this is kind of like a nice, easy example to go ahead with. So first, we have seen that there's this parameter S, which actually determines the flavor, the CP symmetry. You might think that our results could depend on this parameter S. So the results for the charged lepton flavorization, it turns out to be not. Let me just, if you want to see this explanation later, I can explain you. But it turns out to be not. So we will set this S to 1, and actually you could put it this way. With the help of charged lepton flavorization, we won't be able to determine which is the CP symmetry chosen by nature if we see something. It's just independent of it. Now let me go order by order, in the sense that I would like to show you first results where we actually only inspect the dependence on theta r, more or less. So which means we fix the two scales which we have to some value, which is meaningful, but not particularly like the best value of all, but just some typical value. Then we have the different lines here, which are for different values of the theta r. And here on this axis, you see the theta L, actually, the other angle. And then you see the results for mu2 gamma. So you see mu2 gamma, if you take the future bound, which we expect from MAC, you see that there's some parameter space which can exclude. You see first the tendency that if you go to mu2 3e, as the experts among you would have expected, usually this gives stronger constraints. So it can exclude more of the parameter space which we have. And then if you go to mu-E conversion, here we take as example the COMET future bound. Also there, the exclusions are going to be very strong. So now you could say, oh, look, if I'm sitting here, then I would be good with COMET, and also with the others I would be good. Now, what you should not forget is that this theta L, actually, we got to use it in order to adjust the lepton mixing parameters, the lepton mixing angles, according to how these have been measured. So you see here these very thin lines, I mean, these very thin areas, which are in different colors for the different values of theta r. Only in here, if you only if you're sitting in here, you're okay also with the lepton mixing angles. So immediate conclusion over here, either you are good with a charged lepton flavorization or you're good with the lepton mixing angles, but not both at the same time. At least not for these values of mu0 and m0. Just to show you the interplay of the different observables which we have. So let me go on now. Let me say, I'm not going to be that strict. I don't want to fix the M0 anymore. I want to keep the M0 free to show you also how our results, so the branching ratio and the conversion rate, depend on the M0. Still, I keep the mu0 fixed to 1 kV. So here, the theta L actually is always fitted to the best fit value. So the lepton mixing angles are okay. So then we now study only what is kind of the variation of our results with the M0 and with the different choices of theta R. And you see here, actually, yeah, the theta R decides a bit on whether you're in or out with the mu2 gamma bound. But for the M0, it's very flat. It's hardly any dependence. You see a bit more this effect for mu2 3e, and you see again that this has stronger exclusion potential. Now for the mu-e conversion, I just want to show you this plot in order to prove here that we find again the cancellation, which I was already saying that this analytically, you find that this should be there, and indeed, if you make such a plot where you plot the conversion rate with respect to M0 for some fixed value of mu0, but varying this theta r parameter, you see that it always going to have an exact cancellation at this around 6.5 TeV. And you have to be really near this cancellation in order to be in agreement with the mu conversion. But if you are at that point, you go back to the slide which I've shown you for the mu3, and you will say, okay, but then mu3 is going to kill me because I'm out of the, I mean, I should be visible for the mu3 experiment. That in conclusion actually just tells you that this mu0, which I've chosen here, is probably a parameter which is not in the preferred parameter space, which can satisfy all bounds. So what we did then last, we actually were scanning over the parameters which I was showing you before, this range for the M0, this range for the mu0, and keeping the theta r free. Always fixing the theta L such that the lepton mixing angles are fine. And then here you go. That's what the result what you get typically. So you get a panel with the 2 branching ratios and 1 conversion rate, then with respect to M0 or mu0 or theta r. So let me first, so now you see many colors and many stuff. So let me first tell you, ignore the gray, the orange, and the red points, because they are for different reasons already excluded, either by current bounds or by the future bounds. So the future bounds on mu-e gamma, mu2,3, or conversion rate. So then only look at the points which are colored according to this color bar here, so between blue and yellow. And here, what do we use as quantity in order to kind of give a label to each of the point? That's an average Yukawa coupling, so to say. And then let's come to the observations regarding the parameter space. So first of all, we see there's no parameter space in M0, which we generically exclude already. We see that there's the cancellation. Even in the scan, the cancellation becomes visible. For the mu0, we see that there is generic tendency telling us that mu0 should be larger than 2 keV. Otherwise, we will always be hit by some bound. And then for the theta r, as I was saying, this to us is a totally free parameter, and you can expect anything. What could happen? And here it turns out to be that the theta r really can push a lot the branching ratios and conversion rate, or it can suppress it. So then you ask yourself, how can I get such a dependence? Funnily, it's actually like a cosine of 2 theta r. And then you look into it more closely, and you see that there is a light neutrino mass, which goes like the Yukawa coupling times cosine, or the absolute value of cosine of 2 theta r. So if you suppress the cosine of 2 theta r, you add a value where cosine of 2 theta r is very small, then you need a largish Yukawa coupling in order to get the light neutrino mass as you want it, which means you push the Yukawa coupling. Pushing the Yukawa coupling to a larger value gives me then the larger branching ratio and the larger conversion rate. So that's the point. That's the direct inference which we see, and the interplay that everything is connected. Okay. You can ask also now, let's talk about the experimental prospects. So we actually see that in the parameter space, which is allowed for us, we hit the comment bound, we hit the bound of the mu3e phase 2. And then if these bounds are okay, or we are below these bounds, then you can ask yourself, but what's the maximum what you could reach still for mu3 gamma? And there's kind of sad news for the MAC2 experiment, because this is about the maximum value which we get is about 2 orders of magnitude below what they foresee as their future sensitivity. So that tells you rather that these two types of experiments are just much stronger if regarding to prospects and constraining the parameter space. Obviously, it might also be nice if they have a positive signal, then the story changes, but we were assuming just the bounds. You can ask yourself now, you could spot here that I was presuming all through here that light neutrino masses are normally ordered and that the lightest neutrino mass is 0.03 electron volts, which means this fixes my Yukawa couplings. you could ask, do things considerably change if I change that, given that we don't know the ordering and we don't know what the lightest neutrino mass is. We studied this also, and we studied different values of the M0, and generically we found very much the same picture. So that's not strongly changing. You can also compare, if you like to make some sort of comparison plots to see which is the strongest experiment, has the best potential. Again, you just confirm what we have seen before. The best prospect actually, or the largest potential is by far the largest from the mu-e conversion experiments. So I have very high hopes on this because they really efficiently can constrain the parameter space. I mean, they don't rule this scenario out, also this example not, but they can effectively constrain it. I think I will mostly jump over case 2 because the hour is already over. I would like to show you one thing, because we observed for this case 2, there are also some versions where it actually there's no dependence on this theta r, and we have others where there is dependence on theta r. But maybe this is not what really excites you. What you could actually rather look to is the left-hand side, because there you see that what we observe for this case 2, this other type of lepton mixing pattern, is actually that we get some sort of, in our scans for the parameter space that we scan, we get lower bounds for mu3 gamma, but also for mu to 3e, and also for mu-e conversion, as long as we're not sitting very close to this cancellation. As you now look at the numbers, this is 10 to minus 19, this is something like 10 to minus 21, and this is something like a bit of 10 to minus 22. These are all far below what the experimental next round foresees, but still it's interesting to observe that you can't suppress it arbitrarily. So there is a sort of lower limit in this examples which we have here. So, and this is true also whether you have or not dependence on this theta r parameter. It just looks a bit more fuzzy if you have also this dependence on this theta r parameter. But that's what you rather would expect if you have another parameter which gives a bit more variation to it. Let me jump to one last thing, which you might, if you don't like mu-e transitions and you're a bit bored, you might ask at least what happens. Could there be anything interesting happening with the tau? So we studied also this for a different tau decays. Short answer, I'm very sorry if you like tau leptons a lot and tau cLFV a lot. As long as you satisfy all the bounds which come from the mu-e transitions, the results for these 4 branchings are going to be 10 to minus 14 or less. And as you know very well, the prospects for Bell2 are around a bit times 10 to minus 10. So we are orders of magnitude below that. So we don't expect anything interesting coming from the taus here. Yeah, and that let me just maybe go to the last slide already by saying, I hope I could tell you that there should be an organizing principle, in my opinion, somewhere in the lepton sector. And I think this type of flavor symmetries, these non-abelian discrete things are very interesting, in particular if you combine them with CP, because they're then also highly predictive. I like the inverse seesaw mechanism a lot because it has potentially large pheno. It's very simple at the same time, but it has a large pheno. And when you combine these things, usually you have different possibilities, which we saw now, these different options, which tells you where actually your flavor structure is non-trivial and which type of mass matrix, which we have seen. And depending on which you have, if you encode all the non-trivial flavor structure for the neutral states in the lepton number violating part, we have seen that actually cLFVs are really out of reach. They're much too suppressed. If you indeed go to the scenario where your non-trivial flavor structure is in this Yukawa type matrix, so the connection between the left-handed lepton doublets and these end states, then we see get a lot of signals, and indeed we are going to be much constrained by experiments like mu3e and the mu-e conversion experiments comment and mu2e, which are all coming up in the next 2-3 years. Yeah, and then seeing these different types of results and the different possibilities which you have to constrain such scenarios is obviously interesting to to think about more options and to think also about variations of it. So I was very conservative by having 3 states of N and 3 states of S. Obviously, you can also vary this, and you can say what happens then, and you can study the different pheno and compare and see your possibilities to actually learn something, which kind of variant could be realized, which kind of these symmetries could be realized or not. Okay, so thank you very much.
Thank you very much, Claudia, for the very nice and very complete talk. Question from the audience?
Hi, I have a question. So first of all, thank you for the nice talk. So this might be a silly question. I missed one point. So which was the source of the complex phase? Because it seemed like you were taking real Yukawa coupling. So the only source is the omega matrix.
Yes.
Okay.
So
okay. So that
I actually can show you one omega matrix. I was jumping over it, but just to show you one example for this omega matrix, you get to see one omega matrix here, and you see that this actually has a face, and this is a face that you can't factorize.
Okay, so this just one phase like 5s is enough to okay.
This is for case 1. Okay, the omega matrices for the other case is a little different, and then the structure is richer.
Okay. Yeah, thank you. So, okay, this also indicates that the Yukawa couplings are real for the...
I mean, it's not an assumption. This is what it comes out.
Yeah, it indicates. Sorry. It implies the symmetry. Okay.
So, I mean, if you talk about the Yukawa couplings in the sense that you talk about this Y1, 2, 3, yes, these things are always real. So if you see here, this is the most general structure of this, I mean, for this option 2 of this YD. And then if you ask now, what are the sources of the faces, then they sit in the omega, and this omega of this 3 prime, while you have here rotation matrix, which is around this angle theta L, and there's another one around this angle theta R. This one is just a permutation matrix. So all this stuff here in between is real, and you can show it. So this is not an assumption. So this is
Okay, so I was just wondering. I mean, like if you consider scenarios like resonant leptogenesis, it will be like very restrictive or predictive, like maybe because.
I mean, you can look at leptogenesis, yes, for sure. I mean, this actually you have source of CP values. I mean, there are phases, non-trivial phases, and you have seen showing your examples where sine delta is not 0 or sine beta or sine alpha is not 0. So you do have that. I mean, regarding leptogenesis studied in this inverse seesaw, I think it would be very interesting to do. This has not been done in the relation with this flavor and CPsymmetries, at least not in this generality. We have some work where we actually were looking at this, but in the context of a low-scale type 1 seesaw. So there, this matrix YD also appears. It has a very similar structure, and we were showing that, yes, you can have successful low-scale leptogenesis, so meaning resonant leptogenesis or ARS leptogenesis. And you get, indeed, a correlation between the amount of BOU you generate and the sign of the BOU and the sign alpha, for example, the sign of the Majorana phase. And this also is true in some now older works where people were looking at type 1 seesaw high-scale leptogenesis, yes.
Okay, yeah, thank you.
More questions from the audience? I had one common question. Maybe to implement this resonant leptogenesis, I think we may need a hierarchy between these heavy pseudo Dirac lepton states. So maybe there should be some mechanism just of breaking these some of the symmetries in the neutrino sector. Maybe we'll
I
require extension of the scalar sector to make a different matrix than the capital M matrix that you show with the 1 entry, 2 3, and 3 2 entries to be equal.
You're worried about the fact that the spectrum of the pseudo-Dirac state is very much degenerate.
Exactly.
I agree with you. Yes, I agree with you. There might be, so I can tell you from my experience with this low scale type 1 seesaw that we had certain instances in which we need some additional source of like some splitting, which gave some more splitting to it. But we also had some rare cases. There seemed, for some of this case 3A and case 3B1, it was possible to do it even without introducing an additional splitting at the Lagrangian level. So the splitting you would effectively get would come then from Higgs corrections and thermal mass corrections. In this low scale scenario, you can get that. Regarding the inverse scenario, since we haven't studied that, I can't answer you. I can say it might well be that you need some extra source of this splitting, yes. But then it would also not be, to be honest, it would also not be, how to say, a big surprise, because as you know very well, when you build a model and you put in some flavors in order to write down really the mass matrices and then break the flavor symmetry spontaneously and so forth, you usually get some corrections. So you can think about that there might be some correction, for example, to this matrix, which actually gives you everything that degenerate, that there's some correction which comes from the charged leptons, for example. So that there's a flavon which actually should give masses to the charged leptons, but that is a certain point also coupled in here, which then, because the residual symmetry is different, will definitely introduce some splitting.
Some higher order correction, maybe higher order dimensional operators that may break.
So it's not going. I'm not talking about order 1 splittings, but you could imagine something. If a few percent are sufficient for you, then it should be doable, I think.
I see. Thank you, Claudia. Thanks a lot.
You're welcome.
I have a quick question, if I may.
Sure.
Yes.
Regarding the phenomenology of lepton flavor violation, have you analyzed anything with muonic atoms?
No.
How to compare it with the other channels? No. Okay. Thank you.
Any more questions from the audience? Seems that there are no more questions. So we thank Claudia for the very nice and very complete seminar. Thank you so much, Claudia.
Thanks a lot for the invitation. Was a pleasure. I hope you enjoyed the seminar.
Yeah, very nice seminar.
I mean, I'm also happy to answer via email or anything. Yeah, I would say it was nice to see you online again, Antonio, maybe next time even in real life. And yeah, have a good day. For me now is evening, and a good time. Bye-bye.
Thank you, Claudia. Same to you. Hope we can meet soon. We will have a conference here in Chile, the annual conference in January, High Energy Physics Workshop in the week of 6th of January. It will be nice if you can participate.
Okay, let's see whether this is compatible with my teaching and with the exams which I have to do. So that's good. Good to know. Very good. Okay, perfect.
Thank you so much.
Nice day. Bye-bye.
Bye.
Bye-bye.
Bye-bye.
Bye.